Oh, don't be getting us in trouble now.
5 seconds. Okay. We'll be taking care of business here tonight with Eric Kaiser.
Evening, Bill.
How are you doing, Eric?
Everybody out there watching. I'm good. I'm good. How are you?
I'm doing great. I'm wearing my live stream shirt tonight again.
Awesome. Very nice.
Courtesy of Doug Kroll. Doug, thank you. Many thanks.
Thanks, Doug. We appreciate that.
So you were queued up here to talk about refrigerant recovery best practices.
Yeah.
Yeah. Hey, do you know any worst practices?
Yes.
Do you want to cover those first, or do you talk about them in your session here?
Well, I've never thought about talking about worst practices, but I mean, there's a few in here. There's a few in here I talk about.
All right. Let's make sure we cover those too.
All right.
Make sure reorient people's thinking.
Worst practices.
Yeah.
That would be a good title. Refrigerant recovery worst practices. I don't think I've ever discussed worst practices just like with a focus on that before.
No.
So, well, how's your week going?
It's coming to an end. It's Thursday. Really looking forward to the end of it. I've undergone some physical therapy for a shoulder injury, and just got me like going, round the clock here. So I'm happy to see the week come to an end, and happy to be traveling next week and be traveling with you to Building Science Summer Camp.
Yes.
Nerd Fest for people in building science.
And you're going to see Doug Kroll there, so you can thank him again for the shirt.
I will. I may even wear the shirt again. I'll have to wash it though, but
you got a couple days.
Yeah.
You can get it clean before then. So, well, you got any questions I should cover? Anything other than worst practices that I should cover? Any questions you think you might have or the audience might want to know about?
Like, when do you recover? Like when is it appropriate to recover? So just so you know, we're queued up with the right timing. I looked up a little article here. It's an old one, and it said there's 3 stages during the life cycle of refrigeration equipment that you recover. So
all right, I'll bite. What's the article say?
This is from the news, ACHR News. It's from 2010, but I think physics hasn't changed too much since then.
Not typically, no.
Okay.
It doesn't. There's not been a lot of real big discoveries in physics since then.
So during servicing, when a partial or complete charge is removed from the system. Second, when the system's converted to run with the new refrigerant. And third, when it is scrapped and disposed. And maybe that leads into a worse practice.
Any one of those could lead into a bad practice, such as not recovering the refrigerant, yet getting it out of the system.
Yeah. And is this not respective to any particular size system, refrigerant recovery? I mean, you're going to cover a certain size of systems?
Well, I mean, realistically, any size refrigerant system needs to be recovered. Now, the caveat to that is if you have a hydrocarbon refrigerant.
Mm-hmm.
So the hydrocarbon refrigerants like R290, R600, R600A, those are deemed, and CO2 also as well, which is not a hydrocarbon refrigerant. But the ones that are deemed as natural refrigerants, they're naturally occurring, those we don't have to recover. It's all the other ones. It's the fluorocarbon refrigerants, as they're deemed, that is what we need to recover. That's what we need to get out of the atmosphere. Those are the ones that they're finding are harmful to the atmosphere, harmful to us. In the long term, it's harmful to us.
Got it.
Whether directly or indirectly.
Okay.
So, and those are the ones that are regulated in the United States under the EPA's authority through the 608 certification.
Right. And 609 for mobile.
Correct. 609 for mobile MVAC, mobile HVAC.
Right. And you're talking mostly stationary right now?
Yeah, we're talking about stationary in this. The practices are similar a lot of times, but Actually, the mobile stuff is really pretty automated because the mobile stuff comes into a shop and they oftentimes will have a cart that they can just wheel over, hook up, push a couple things on it and start it up and walk away. And it's much more automated than what we get anywhere else with the stationary equipment, because the equipment is stationary and we really have to bring in a whole setup and tanks and everything else, which makes it a little bit more difficult at times.
And usually higher volumes than an MVAC.
Yes, much higher volumes typically.
Okay.
So
All right.
we've got to have a lot bigger tanks than what's typically dealt with in the MVAC systems.
So preach.
Preach. Okay, here we go. Let's go. We're going to do refrigerant recovery best practices here. I'm going to make a quick adjustment. Let's see. There we go. There we go. That's what I wanted to do. Okay.
Yeah, I got a big head anyway. Don't need to make it any bigger. Smaller is better.
Bill's going to hang out over here. There he is. He's over there.
Yep.
He's going to hang out over there and answer your questions. So if you've got anybody watching live, throw your questions into the comments on whatever platform you're on, and they'll pop up there. Bill can call them out, and that way we can get some questions answered.
Do I need to be logged in?
Looks like there's 3 viewing up there.
I don't think I'm logged.
A 3 up on the top left corner of your screen there?
No, I don't.
Oh, okay. All right.
I'm going to try to log in. So if I go away and come back, you just keep going.
I'll keep rolling.
All right.
Okay. So if Bill disappears, everybody knows why. I'm going to keep on rolling here. Anyway, so refrigerant recovery best practices. The topics we chose for tonight, we're going to talk about different types of machines. We're going to talk about filling tanks safely. This is a really big one. Accessory selection. We're going to talk about speed, trying to get that sped up, A2L compatibility, some other things in here. So we really want to give people best practices of doing this. And as Bill mentioned, maybe some worst practices. We'll talk a little bit about those as we go through. So whenever Bill gets back, he may jump back in here. But without Bill, we'll just keep rolling along and we'll get this done. And again, I've still got all the comments up on the screen. So if you're watching, you got questions, pop in there, let us know you're watching, and ask any questions anytime. All right. So the standards that we have for refrigerant recovery, really that's EPA 608, right? It's the refrigerant types. They define the types that need to be recovered, the level they need to be recovered to, the record keeping requirements, all that stuff's covered in 608. And then we have AHRI Guideline K 2024, because that just got updated in 2024, which is containers for recovered fluorocarbon refrigerants. Okay. And it looks like Bill's back, so we're gonna bring him back in here. That way he's watching over me, can ask any questions. If he's got questions, he'll ask them away as well, because Bill's really sharp. He comes up with a lot of good questions. He's been around.
Yeah, that's no lie there.
Okay. So 2 basic types of recovery machines. And this changes the type of compressor that's inside the recovery machine, because what we're using is a compressor or a type of pump to move the refrigerant from the equipment into a storage tank. Right? And sometimes we use it to move it from the storage tank back into the equipment, but most of the time we're just using it to go from the equipment into a storage tank, storage vessel of some type. Right? So we have 2 different types. We have a horizontally opposed, right? This style does not put any refrigerant into the crankcase. All right. And this is the style that's going to be used on any machines that don't have a purge cycle. So I kind of divide the machines into 2 types. You either have a purge cycle on the machine or you don't have a purge cycle on the machine. And the other type is the type that's going to have a purge cycle on the machine. And the reason it has a purge cycle, a lot of people mistakenly think that the purge cycle is to remove the refrigerant out of the hose between the machine and the tank. Now, sometimes it can push some of the vapor out of, or some of the liquid out. If there's any liquid refrigerant in that, sometimes we'll push some of the liquid out of that, but it's not going to get rid of refrigerant in that hose. It's not there to do that. The purpose of that purge cycle is to clean refrigerant out of the crankcase, because just like a hermetically sealed compressor that we use in our systems, okay, in this style, we run refrigerant in through that crankcase. So that's kind of the two different styles. Now, whichever style you use, some of them are faster than others. They have different capacities. Whatever style you choose, make sure that you read the owner's manual and understand how that machine works, because there's differences in each machine, how the manufacturer recommends them to operate. We're not going to get into a lot of specifics on that. We're talking about generalized best practices here. When you get into machine specifics, you really want to dive into that manufacturer or call us. We can help you with machine specifics as well, because there are some differences between the machines. But most of the time, we defer to the manufacturer on that, because they're the ones that make the devices. Okay, so internals, two different styles, and that's all going to be on the knobs on the front of the machine. You're going to be able to see one's going to say, one's not going to have anything on it for a purge, and one's going to have a purge setting typically on a large knob on the front of the machine. Okay, when recovering, it's important to know whether we are recovering liquid or whether we're recovering vapor refrigerant. Now, when we're recovering, we typically like to recover in the liquid state as much as possible. We want to keep that refrigerant liquid if we can, because that goes faster. We can pump it quicker, right? And we can see this right here by our density. So this is pounds per cubic foot. How many pounds per cubic foot? And you can see that even liquid refrigerant changes density with temperature. This is one of the reasons why you'll see lower capacity at higher temperatures, because the density reduces on that refrigerant. So we can't move as many BTUs. But what we're going to see here is, if you look at R410A, we're just going to use that as an example on this. At 75 degrees Fahrenheit, 66.7 pounds per cubic foot of refrigerant, versus 130, it's 54.7 pounds per cubic foot of refrigerant. Now, if we flip that over on the gas side, and we're looking at the gas densities, right, at 75 degrees, we can move 3.9 pounds per cubic foot, or at 130 degrees, we're moving 9.9 pounds per cubic foot. And that doesn't make any sense. And I think I screwed something up on that slide there. We may have to revisit that one. But this is what happens sometimes when I pull up an old presentation and put it together for this. Didn't quite proofread everything. I think those two are reversed. I think those two numbers are actually reversed, if I'm remembering correctly in here. So anyways, it changes. The point is that it changes. And it's a lot faster to do the liquid than it is to do the vapor. We're going to get it into that tank. The other thing is we have to condense it in the tank in order to fill it, because we can't shove all the tank full of vapor. And if we try to shove that tank full of vapor, it's going to get really warm, because it has to reject the heat. We're going to talk about that in a little while. Okay. So there's a couple different ways to move refrigerant out of a system. All right. We can do what's called direct recovery, which is where we hook the machine to the system. We pull all the refrigerant through the machine and we put that in the tank. That's direct. The other method is going to be push-pull. Push-pull is typically used on larger systems where there is a large volume of refrigerant to recover, and where we know that we can access liquid refrigerant in the system. And with push-pull, we connect the liquid, wherever the liquid is at in the equipment, we connect that over to the tank, and we put that in the liquid port of the tank. And then we hook the vapor port of the tank up to the inlet side of the recovery machine, and we pull the vapor off of that tank. We run the vapor through the machine, and we put the vapor back into the system to push that liquid out of the system. Now, at some point, we're going to run out of liquid, and we have to switch from push-pull over to direct. So at some point in time, we're going to have to make that change. And when we do, it's a good idea so that you're not purging, not having to repurge all your hoses if you have valves on the end of your hoses. And then it's a lot easier to switch over. Okay. All right. Let's talk about tank filling. It's very important to understand what these numbers on this tank mean. And these are two very important numbers. WC. Bill, what do you think WC means?
Water closet.
Water closet. That's a great guess. And it does actually mean that, but just not in this case.
Okay.
It's actually water capacity.
Yeah.
Okay. And that's water capacity when that tank is 100% full of liquid water at a specific temperature, typically at 75 degrees. So it's going to hold 26.1 pounds of water. Right? And the tare weight, or TW, is tare weight. That is the empty or dry weight of that tank. So that means it doesn't have any refrigerant in it. It doesn't have any oil in it, because these tanks can get oil logged, because when we're recovering, we may be pulling some oil out as well. So the dry weight of that tank with nothing in it, a good vacuum pulled, is going to be 16.1 pounds. All right. So these are two very important numbers to understand when we fill a tank, because we don't want to overfill tanks. These tanks are going to be in vehicles that we're going to be driving down the road typically. A lot of times they might be inside the vehicle with us in the case of a service van. If you use a truck, they may be outside. But if it's inside with you, or if it's outside, you don't want to be rupturing that and losing the refrigerant, because this refrigerant in a lot of cases today is worth a decent amount of money. It can be. Most of the reclamation facilities, so reclaiming it is taking the recovered refrigerant. So we as technicians recover the refrigerant, and then we would send it to a reclaimer, where that reclaim company takes the recovered refrigerant, cleans it, reconditions it back to new condition. They are the same rating between new and reclaimed refrigerant, and puts it back into inventory so that it can be used again. They close the loop on it, basically. So we want to return all that refrigerant we can. So if we overfill this tank, we can get a rupture on it. We can get the relief valve kicking off on it, and it's going to vent the refrigerant. And we don't want that refrigerant venting at all. We really don't want it venting inside of a hot vehicle. So we need to know how to fill this properly, because if we overfill them, there's a greater chance it's going to spill or rupture and leak inside that vehicle if we're in it.
And you don't have to guess about the weights. You can get a scale.
Nope.
Scales come in a lot of different price points.
Lots of scales out there.
Yeah, right.
Lots of good scales. Lots of neat features on scales. Wireless scales. Scales that hook to
ports to charge
up to Bluetooth, and will have valves on them, do all kinds of neat stuff nowadays. Right. Automatic charging, all kinds of stuff. So a lot of features out there you can get.
Cool.
Now, we have this cool little chart here. This is what the whole thing looks like. I'm going to zoom in here on the next slide.
Please.
Zoom in a little bit there on it. This one I actually just recently redid, and I don't think it's live on our website yet, but that'll be up and live in the next few days on our website. So what this is a chart that gives you the calculations to figure out what the density of the different refrigerants are. So what happens is the refrigerants are different densities. Now that tank, as we know, was rated in water, okay? And if we have a refrigerant that is lighter by volume, so we're going to pick on, let's see, what are we going to look at here today? We're going to look at R454B, right? That's a new refrigerant that's coming up. It's going to be used widely in the industry. So it is 0.83. It's 0.83 of water. So we consider water a 1. And it's 0.83 of water. So it's lighter by volume. So it's going to fill the tank. But if we don't weigh it properly, we're going to overfill that tank. And
So
the
it'll
tank,
fill it at a lower rate than that water capacity rating.
the rule on the tank filling is we want to fill them to 80% by
80.
volume.
Right.
But if the weight is less than water, and I say I'm going to put 80% of that, whatever the water capacity is in there, and I'm down here, I'm getting close to filling that tank liquid full, which is not going to be good because there's no expansion room in there. And then if that tank fills up, say I set it in the back of my truck and it's in the sun, maybe it's in the back of my van that gets up to 120, 130 degrees in the summertime, just sitting there. Well, we need to have head space in that tank so that that refrigerant can expand a little bit and not overpressurize the tank.
So that's a question that came in. Why do we need to be worried about recovery tank rupturing in hot weather?
Right. So one, if the overpressure relief valve is working, it's going to vent it. If it doesn't work, I'll show you what happens here in a minute. I got a really nice picture of that. So what we do is we use we find the refrigerant type we're working with. I put a lot of common refrigerant types on here. Gives us a refrigerant multiplier. It also gives you the density at 130 degrees because that's where we consider our 80% at. If we're going to store it in a temperature over 130 degrees Fahrenheit, there's a note down here on the bottom that says we want to go down to 60%. We want to reduce that fill down to 60% if we're going to go over 130 degrees.
Where did you get all this logic from?
So all this information came from Guideline K.
Oh, what is that?
Well, we talked about that when you were gone.
Okay.
It's AHRI Guideline K.
I'll watch the recording then.
Thanks for joining us, Bill. We appreciate it.
Pleased to be here.
But anyways, yeah. So that's all laid out in there how this works. And I went through that the refrigerant densities are actually surprisingly hard to find. And this is a part that's often skipped when we're talking about recovery best practices, is that density calculation. So what we do to find the max refrigerant in the tank, or what I call the MRT, is tank water capacity times the refrigerant multiplier times 0.08. Right, and it's all laid out on here. There's examples on the bottom of the sheet. There's also an online calculator available. Brian Orr on the HVAC School website and the HVAC School app have an online calculator in there. Now, that calculator doesn't have a full list of the densities in there. So that's one reason why I put these densities over there. So if you want to use that app, you can actually go type in the actual density of the refrigerant at 130 degrees, and that will tell you, it'll do the calculation for you if you don't want to do the calculation manually. So a couple different ways to do it. And there are a couple of, there's a couple other apps out there that I'm aware of that actually have the calculations built into them as well. So look around at your favorite tool app. A couple of the smart tool manufacturers I know have put that in the app as well. So that's how to use that sheet. Now, what happens if we don't fill that tank properly and the relief valve doesn't happen to work properly? Right? We end up with this. Now, you can see that tank split down the side, right along the weld seam, weakest point of the tank. The interesting thing to note about this tank was sitting in a distributor's warehouse, right? And that tank started out on the other side of that wall when it relieved. Thankfully, nobody was nearby. Nobody got hurt. But I can't imagine what that noise made, number one. And number two, I can't imagine what would have happened if this had been in the back of somebody's truck when that ruptured. So it was really lucky about where it happened, but it was a great reminder about why we have to make sure we fill these tanks properly, and we do not want to overfill them. We do not want to overfill them. We got to be safe about this, because this is a pressure vessel that we're not only carrying around, but we're also putting on our trucks and driving around. And if something like that launches out while we're driving, number one, you're going to be pretty distracted by that, the noise, the cloud of whatever coming out. If you're inside your truck, you may have your windows rolled up and the air conditioning trying to cool down up in the front of the van or something like that, and that goes off in the back. And now you're in an enclosed space with a gas that is rapidly going to deplete the percentage of oxygen in that space, and you're operating a vehicle at that time. So not a great place to be. You need to get that window down quick and get yourself some fresh air if that ever does happen to you, and you have communication between the refrigerant storage compartment and your driver's compartment. I like to say, play like your Ace Ventura. Hang your head out the window. You know, maybe not quite with all the weird stuff that Ace Ventura does, but you know, you'll let somebody know. Make like a, you know, he makes that siren noise, right? Tell everybody, get out of your way. I got to pull over. Okay. Let's talk about damage to the internal parts. All right. So we need to keep these internal parts clean. Now, how do we keep the internal parts of our refrigerant systems clean?
Filters.
We have filter dryers, we have screens, we have all kinds of stuff in there. So it's a really great idea, because what we don't want to do is we don't want to have damage like this. Okay, this is, you know, this one, there's a valve missing here. So there's actually two little poppet valves in that head. That's the head. And there's a valve missing in there. It got broken off completely by something. Don't know what. I'm going to guess that it probably damaged, this is the piston in the same unit, and it probably damaged that piston over here, right? It's got a piston, and it's got damage to the piston and the rings that were sealing that piston going up and down, making the pumping. That unit's not going to work real great. Capacity is going to be reduced on it a lot, because something was allowed in there, some kind of foreign material. And we've all cut open refrigeration systems and found copper shavings, metal, whatever else in there. You might find solder balls. You might find pieces of a filter dryer. Who knows what you're going to find in there. But a lot of times you're going to find some junk. You don't want that going through your recovery machine. I mean, I guess kind of we do, right? We sell recovery machines. We want people to break them and get new ones, right? No? Okay, no, we don't want
good
that.
work. Good
No.
work.
No, we want good quality work. We'd love you to buy your recovery machines from us, but take care of them and use them for a long time.
Yeah.
Buy your first one and just take care of it, right? Again, this is another one where things got really, really damaged inside this machine. This is a compressor, or this is the piston over here. You can see all kinds of scarring in that piston. This is the head, or the top of the piston, I should say. This is the head back here. The valve plate, it's all beat up in here. It's missing a valve. There's got damage in there, right? And the way that we can stop this is really simple. It's called putting a small filter dryer in front of the recovery machine, right? We put that filter dryer in there right here after it goes through our manifold, or however we want to do. If we make, however, we're going to talk about several connection methods, all right? But we want to put a filter dryer in front of that machine. We don't want that junk coming into our compressor on the recovery machine. It's already probably messed up the compressor in the system potentially. Maybe that's why it's dead. Maybe that's why you got to pull the refrigerant out of it. So put that filter dryer in there. It's cheap insurance, right? It's not there to clean the refrigerant up. It's not going to clean the refrigerant up. That's not what it's for. All it's there is to protect your machine from foreign objects going through your machine, being processed through that machine.
Any special type of filter you should put on there?
Just a regular filter dryer. Typically what I always used was a quarter flare dryer, 1/4 inch to 1/4 inch. That way it's easy to hook up the hoses. And you can get a couple little like 12, you can get a little 12-inch hose that goes between the filter dryer and your machine. And then you just hook up your regular refrigerant hoses over here on the other side of that. Or
And
a
these
wide.
last forever, right? These filters last forever.
What's that? No, they don't last forever. I depending on what I'm pulling out, like I've seen some of them frost up on one job because I pulled so much junk out of that it was literally creating a restriction to the point where I was getting that frosting up, which means I'm crossing the
liquid
vapor point, right? I'm turning that liquid into vapor. It's now a metering device. So you can get small ones, big ones, whatever you want to do, but just put it in there. The bigger, the better, because the bigger it is, the longer it's going to last. We're not worried about it drying anything. It's just there to act as a filter.
Got it.
So you want male flare on both ends of that. Okay. And there's a couple different sizes of them. A lot of times recovery machines will also have a screen on their inlet. This is a last ditch effort to keep junk out in case you don't put a filter dryer in there. And again, I've pulled recovery machines apart where this was almost completely plugged. And at the time we were transferring, the worst one I ever saw was where we were transferring from a recovery tank that was kept on a technician's truck into a large storage tank in the shop that the reclaimer would come in and empty periodically. And the bottom, I could shake that recovery tank and hear junk rolling around in the bottom of it. So wow. It's a lesson to maybe not reuse the refrigerant coming out of those tanks, because if you put refrigerant into a tank, even if you've pulled a vacuum on it, you still have this junk laying down in the bottom of it. And that can contaminate what may have been clean refrigerant that you pulled out of a system if you put it back into a system to try to make it work again. So I used to do that a lot, and I learned a lesson there, and I'm like, maybe I don't want to do that quite as much anymore. Depends on the customer, depends on what they want to pay for, but you have to communicate the challenges and the potential hazards to them. All right, so here's a little question for you. Does a recovery tank make a good heat transfer device? Because this is what we use. We use a coil to transfer heat between refrigerant and the air that flows over it. You think that makes a good heat transfer device?
Not as much surface area.
Yeah, not really. Not really. It doesn't have as much surface area overall, and it doesn't have as much surface area in contact with the refrigerant.
And flow too.
Yeah, and you're not flowing through it. So this is a really crappy heat transfer device. So we want, now, if you've recovered much refrigerant, you know that tank can get really, really hot, and then the pressure goes up because, higher heat equals higher pressure. And that's trying to get rid of heat. As you're pumping refrigerant in there, it's being compressed into that tank, and that compression is causing heat, and you're trying to get rid of it to cool it down and keep it into liquid. So before we put it into the tank, we really want to get rid of some heat if possible. And we also want to keep it as liquid going into that tank. So keep that in mind here as we discuss a couple more things. All right. Keeping refrigerant as liquid. This is one of the first really big lessons about keeping refrigerant as liquid. And that is understanding a valve core. Okay, so this is a cutaway of a valve core right here. And this is a closed valve core. As you can see, I don't have anything on this. And this is an open valve core. And the only difference is that this cap right here is pushed down, and all that refrigerant has to come down through this body, all right? And then it comes out the bottom of that body, and it comes over here, and it goes around the edges of that cap in a little teeny tiny opening right there. Versus if we take those cores out, we have a smooth, straight shot through there. Okay, much, much bigger opening. When we talk about the percentage of that opening, 100% open versus this little tiny gap all the way around the edge, and then trying to make that turn and everything. These cores in here make a great, great metering device. They're fine for if you just want to put a gauge on here and take a pressure. Hey, that's great. But when you're trying to flow something through there, get those cores out.
Yeah.
Put that core tool on it. That core tool should go on your connections first. If you're recovering, you're going to do a repair, put that core tool on there, pull that core out, and we'll talk about where to connect the hose onto the core, because this is something I see a lot of confusion over sometimes. But just
and you got a lot of choices today for core tools too.
There are a ton of choices out there.
No excuses. I mean, prices vary quite a bit, features vary, basic functions all the same.
All over the place. But you put core tools on there and you keep them on that system all the way through the repair until after you get done with your vacuum and putting the refrigerant back into it. Once you put the refrigerant back into it, then you put the cores back in and take the core tools off. Other than that, the core tools should stay on the system throughout that entire process, because they're your manual access valve. They take the place of this. This is an automatic access valve. Now you have manual control with a ball valve.
Right.
Okay. So there's the difference between a core right in there and no core in there. It's a big percentage difference. And of course, we got a nice scale up there so you can see kind of the sizing of it. All right, there's a couple different manufacturers of core tools. You can get them in 1/4 inch, 5/16. And this is an old picture. I don't have pictures of a lot of the new ones. I can't even count the number of manufacturers out there today. So with that, find some you like. I recommend finding some that are vacuum rated so you can pull your vacuum through. That's my pitch on core tools. Now, another restriction is hoses and hose sizes and fittings. Right? At bare minimum, those cores are the first thing you want to pull out. So we've got 3 different hose sizes. This is 1/4, 3/8, and 1/2 inch. Right? But this was something that I didn't understand until I started cutting apart some hoses and went, that's interesting. So inside the 3/8 hose right here, I believe this is a 3/8 hose fitting that I cut apart. The inside of that is actually a 1/4 inch. And the inside of that 1/4 inch hose fitting, because this is a barbed fitting that slides up into the hose and then is crimped around the outside with a ferrule. So this has to be smaller diameter. This is only about 1/8 of an inch inside that hose fitting. So again, it's another restriction point. And we get a lot bigger hoses depending on what you want to do. Bigger hoses are going to equal less pressure drop, just like with duct work. Larger is going to be less pressure drop. We can flow more faster through there. And if we don't have that pressure drop, we don't run the risk of getting closer and closer to the boiling point, which means we don't flash to vapor. We can keep it liquid easier, because every little pressure drop can add up in that. All right. Core depressors. So if we take the valve cores out, we no longer have a need for core depressors in the end of a hose. And as you can see here, this has got a core depressor in the end of it versus no core depressor in the end of there. Again, it's another restriction. And when we start adding things up, we get more and more restrictions, or less and less restrictions, means better flow through the hoses, less chance of hitting our boiling point or saturation temperature, and better chance of keeping things in the liquid state. So it's a couple things to try to illustrate and show what we can take out. And this is one thing I recommend, having a dedicated set of hoses for refrigerant recovery. When I'm on a job, I have a dedicated set for recovery. I have a dedicated set for vacuum, and I have a dedicated set for charging. That allows me to keep the hoses that I'm using for recovery. I can take the core depressors out if I want to. And I don't have to worry about using them on charging, because my charging hoses, I want to keep those clean. So if I'm running nice clean refrigerant through it, I'm not running also through the same hose that I just use as a recovery hose and maybe have old, nasty, acidic, junky oil or anything like that in, I'm not blowing that nastiness right back into the system I just tried to fix.
So the color of the hose doesn't control any of those factors, does it?
Color of the hose doesn't mean anything.
Okay.
You can use purple, green, and let's see, what's another color we want to use? How about
Brown?
brown? Yeah, there we go. Purple, green, and brown hoses. If you'd really like, they don't care. It's kind of like wire colors. They don't know. Those are just visual cues for us to know where to hook them up at.
Yeah.
They're all rated at the same pressures. All right. So we got a couple different ways we can hook things up. This is the basic way. We want to put our core tools on here on the system, right? Our vapor, our liquid, with a manifold through our filter dryer into a recovery machine, out of the recovery machine, and we can put it into the vapor port of the tank if we want. Okay. Well, that's going to cause that refrigerant to blow down in the tank, and it's going to come out of a small hole and it's going to expand. So if I'm pushing liquid into the top of that tank through a small passageway and it immediately hits a tank where it can expand, it comes into a wide open area. What do you think is going to happen to that refrigerant at that point, Bill?
Cooling,
It's going to cool,
flashing,
but it's probably going to flash too. There's a good chance of it flashing because there's nothing containing it other than some other gas in there, and that gas is going to be squishy.
Mm-hmm.
So if we blow liquid in there, it's a good possibility some of that may immediately flash to gas, especially if this is a lower pressure, because this has got to be a lower pressure in order for us to push refrigerant through here.
Yeah.
Because this is your lowest pressure point. Otherwise, if the pressure is all the same in here, then we're not going to be able to move refrigerant into there.
Nothing flows.
Right. So we're going to talk a little bit more about that as we go along. And one of the big things too is anytime you're filling a refrigerant tank, make sure you have it on the scale. Do that calculation, do that fill calculation before you fill the tank up, and make sure you keep it on the scale so that you don't overfill the tank. One of the first times I saw a tank relieve in person was a job where I was working with a friend of mine, a coworker, on a roof, and he was working on one unit. I'm working on a different system. And the system he was working on had double the amount of refrigerant it was supposed to in it. So he did the calculation and assumed that it had the correct charge in it. Well, somebody else had been working on it previously and had double charged the system. So his tank overfilled while he was on the other side of the unit doing something else, and ended up with a tank relief blowing out. So make sure you have a tank on there and that you're watching that, have a scale under the tank, and make sure you're watching that so that you're not overfilling your tank, because you don't want to overfill these tanks.
Do any scales come with alarms to let you know when you're reaching that?
There are some that have alarms. They'll hook up to an app on your phone and send you an alarm.
So those are one of those features you can use to improve, rather than glancing at it all the time.
Yeah. You can get wireless heads that come with the scales. The bad thing about the Bluetooth, or the one thing about the Bluetooth, is you have to make sure you're in range.
Sure.
Because if you get out of range of that, it's not going to go out forever. But a lot of them have pretty good range on them. Now, here's your core tools, and where you want to hook those hoses up to is the back side of that core tool. When you unscrew that stem that pulls your core out, that connector that's on there is a male 1/4 inch connector that you can screw your hoses directly onto. And the reason you want to do that is because then that valve will turn this port off. All right? These side ports have a Schrader in them, and you can't manually turn that port off. So that's for putting things like gauges on. Like we want to monitor the pressure in, which we'll talk about that in a little bit here, getting these manifolds out of this, because that manifold can be an added restriction point.
And that Schrader would also be a restriction. So you're kind of defaulting on some of your assumptions here is open everything up.
Yeah. So get it as wide open as possible. The fewer restrictions, the more you can keep things in liquid, And the faster it gets liquid into that tank, faster you get the job done. All right. So one of the first places we can really reduce restrictions, or the first place is reduce the restrictions right here with the core tools. The next best place to reduce restrictions is going to be on the discharge side of your recovery machine. Okay. So get a bigger hose, get a 3/8 diameter hose that's going to go on there and reduce that restriction on the discharge side of that machine. Okay. Now, inside that tank, we have two places we can put refrigerant into. We can either go into the vapor side or we can go into the liquid side, and this is determined by the dip tube in the tank, not by the color of the valves. Blue is not always vapor. Blue can sometimes be liquid because liquid is subcooled. So that would make sense to have it as blue because it's subcooled. But depends on what the tank manufacturer did. Make sure you're reading the valves. Okay. Read the valves. Don't just look at the colors because they don't care. The other side, though, has a dip tube on it because when that tank is upright, it's designed to pull liquid from the bottom of the tank through that liquid valve. Now, that liquid valve, as you can see here, if we look at this, is pretty doggone small on the inside. Not very big. That is a good size restriction on there. And the hole over here for the vapor is a whole lot bigger.
Sure is.
So we can flip that tank over and we can reverse those. If I turn that tank upside down, now this becomes my liquid. This becomes my vapor because it's pulling off the top of the tank when it's flipped upside down.
Mm-hmm.
Okay. So that's another way to reduce restriction.
It'll always be at the bottom because of gravity.
Yeah, because liquid's always going to be down here. We flip that tank upside down, we hook it to the vapor side, and now my discharge, as long as I have liquid coming out, is filling that tank from the bottom up. It's less likely to flash because I'm putting any liquid refrigerant immediately into something that's not as compressible. Right? Because I'm putting that liquid right into that. And once you're done putting liquid in here, you don't want to continue pumping the vapor up through that liquid because it may try to boil some of that off just by the vapor coming in there. So you watch the level of your tank. You watch it rise. As long as it's rising pretty speedily, that generally means you're pumping liquid into the tank.
You're meaning the weight.
Right. Sorry, the weight. Yeah. Watch the
you
weight
can't
on your
see
scale.
through the tank. Maybe you can. I can't.
Yeah. Well, you're watching the weight going into the tank.
Got it.
So the weight of the tank is rising. Okay.
Because liquid's got a higher density than gas.
Got a higher density.
It should be the number should be ticking up faster.
It's going to tick up pretty quick. When that number slows down, that means you've switched from liquid to vapor coming into your tank, and then you want to flip the tank over. Okay. Flip your tank back upright. Now you're on the vapor and you're sticking the vapor in on top of it. That's when your tank's going to really start to heat up. Okay. Because you're trying to condense all that vapor in here because, you know, we want most of that to be liquid.
Is it crucial to try to mitigate that tank heating up, or the?
You can do a number of things. You can put them in water. You can put them in ice baths. A lot of that's really hard to do on your scale. So some scales are rated for water being out in
there's external coils too, right?
Yep. You can also run it through a coil. I got a slide on that. So you can run it through a coil in the line. Speaking of which, there you go. So you can run this through a coil. This is your discharge cooler. So as it comes out of the machine, goes through that subcooler in water or ice or whatever else, or an ice water bath. And that cools the refrigerant down, makes it into liquid before it goes into the tank.
Got it.
One of the things about this is, though, that's not de minimis. So normally, if we have a 4 or 6 foot hose between the recovery machine and the tank, that's allowed to be de minimis, minus the refrigerant that's in that crankcase, because that's too much volume for the EPA's de minimis. This is way over de minimis. So if you do this, you need to do hoses that have ball valves on the end, because in the end, you've got to reconfigure everything and recover the refrigerant that's sitting
in
in
there.
that.
But that thing's got the coolest name in the world, I think.
That is a
I know what it is.
yeah.
Molecular
Molecular
transformator.
transformator.
Molecular transformator. There you go. Yeah.
That's a mouthful.
Right.
But yeah, somebody, and it's an accurate name, but it's a heck of a name.
But a very, very great point about it. It goes beyond the de minimis amounts of refrigerant and needs to be recovered itself.
Yes.
It becomes a container.
Yes. And the purge of the machine is not going to recover that as long as this is on the discharge side.
Right.
You have to move this to the intake side and put a different hose between the outlet of the machine, the inlet of the tank, repurge that hose, and then recover this.
Got it.
Okay. So that's how this looks, right? It comes out of here through the recovery machine, through this sitting in a bucket of water and into this. And then you really want to have this tank upside down because you're going to be pumping liquid in there really, really quick.
And we're not just talking about that particular product, but if it were a coil, would that coil also be holding?
What do you mean by a coil?
Just a coil of copper. Some people,
yeah. So you can just
you
can make that out of a coil of copper. I've seen a lot of people make them out. Make their own. Just get a coil of copper. They wind it around, drop it in a bucket. There's handmade,
but it still defaults on that de minimis rule.
Correct.
Okay.
Correct.
Right.
Because the length here is too long. It's holding too great a volume in it.
Got it. Okay.
Okay. So then you got to reconfigure that. Put this on the inlet side. Flip the tank, and you're going to drop that into the top of the tank on the vapor or on the vapor side there.
If you haven't gone over the weight limit.
Right. If you haven't gone over the weight limit.
Then you might need a second tank.
You might need a second tank. Exactly. Okay. Yeah. That does happen. Okay. So this is a little bit different system where we're going to use a Y in place of that manifold on there. Okay. And this was one I used to keep in my backpack for a long time for recoveries. So I had my filter dryer already set up. I had all my hoses ready to go. It's a quick out, quick in, using 3/8 hoses on there. And this is what that configuration looked like. So I had core tools. I had 3/8 hoses coming over here through a Y through my filter dryer, another 3/8 hose coming into the machine, and then a 3/8 hose coming out to the tank. And to monitor the pressure in the system, because we have to watch that pressure in the system, I would put a stubby gauge or a probe over here on the side port of that core tool, because that's always connected to the system, even after I close this valve.
Sure.
Okay. And now I can monitor the pressure in the system. And I'm doing that on the largest volume side of the system, which is typically your suction side. So there's going to be a larger volume over there. So that's where I'm going to monitor that pressure to make sure that I have all of my refrigerant out of that system, like down to my EPA required level.
What pressure are you looking for?
Depends on the piece of equipment. On typical medium pressure stuff, you're going to look for, I believe it's 0 PSI, but it depends on the type of the equipment and the size of the equipment.
Got it.
So that's all part of the EPA 608. Everybody should know those charts. If not, get a hold of the EPA 608 regs, and it will tell you in there. They have a nice chart for it. All right. And then, again, same thing. Going to put in liquid down here. Once that weight starts slowing down, then I flip my tank upright, throw the vapor on top. I've been told by some people down in some rather warm climates, warm southern climates, South Louisiana, South Texas, that by doing this method, they no longer had to take ice water and ice and things like that up on roofs to cool the tank.
Wow.
By keeping everything liquid going through here, they didn't have to employ tank cooling methods, even in hot summers. So that's, I've never experienced that because I've never worked in that area of the country, but that's what I've been told by people that worked in the area of that country and applied that method.
Got it.
Okay. Now here's your push-pull. Okay, so liquid coming out here, vapor coming here. go through the machine. We're going to keep the machine clean. I don't care about what's going into the tank. I'm going to keep that machine clean with that filter dryer, push that vapor back in here. And this is where I want to monitor my pressure, all right, on that. And then eventually I got to reconfigure that. And again, put all that back in like this to pull the vapor out of that. So even after a push-pull, I still have to pull the vapor out in direct mode. Okay. If you're going to do multiple tanks, and this is really common with the push-pull, you got multiple tanks sitting here. Get a hose. Grab a core tool, works really great for this. You're just not removing the core with it. You're just using it now for an access valve. Pop it on the end of that hose over here on your tank. And when you're done filling the first tank, all you do is you close that valve, close your tank valve. Now I don't have to go repurging everything. And if I do need to purge anything, I open this valve on the end of that hose very, very slightly, just enough to put a trickle of refrigerant out of there, right? Just enough to put a positive pressure on that connection as I'm going to the next tank. That way I'm not hooking it up, putting all my pressure or all my flow capability in there and trying to vent out of this fitting, because those core tools don't have grooves cut down in them for refrigerant relief.
Yeah.
All right. So, and that also works really great for having this on the side, because when you're done, close your tank valve, and now you can use this port here to relieve all the pressure in that hose. So again, little things like that you figure out as you're going along through this, make it easier. All right, A2L refrigerant recovery machine compatibility. Right, that's all decided by UL 60335-2-40. Right, that in there sets forth that recovery machines need to be compatible with whatever refrigerant is being recovered. That's the basic gist of it. But realistically, in the industry right now, this is the only thing that is really being regulated as far as tools in the way of A2L compatibility or A2L approval. A lot of manufacturers have been going back and testing their older equipment, and they're putting out letters saying, okay, this is what you have to do to either update your equipment, or that equipment you already own is already approved for A2L. There's a lot of older equipment out there that they've tested retroactively and said, yep, it's good for A2Ls. So if you have older equipment, if you want to know, go to the manufacturer's website. We have not cataloged all this on ours because it's so changing and so in flux right now with everything. It's not something that we feel comfortable keeping up on. We probably will in the future, but go to that manufacturer's website or call us and we'll get a hold of the manufacturer, and we'll find out if the current or if your existing machine is A2L compatible, so you can use it with the new refrigerants. All right. And
we do have at TrueTech, we've got an A2L badge on products, on new products.
Yes.
That manufacturers have confirmed to be A2L compatible.
Yep.
And I'm just typing in right now. You can just type in A2L and products with those badges will pop up.
Yeah, in our search bar.
Right.
Yeah, internally in our website and truetechtools.com. You can find all that information. We've got a really good A2L resource page on there with a lot of information, and we've cataloged all the tools that the manufacturers have said are compatible with A2L refrigerants. So if you need any of that or you want any of that stuff, just jump on the website. And if you can't find it or you have any questions, reach out to our customer service team, either at the 1-800 number, or email, or chat through the website, and we can definitely get you helped with that.
Yep.
So I think, we timed that perfectly tonight.
Yeah, though. Almost to the minute.
Yeah. So any last thoughts here tonight?
I learned a lot, and I like the way you put things together and explain it out. It's complicated, but it's not complex. But put it that way.
I like
There's a
that.
lot of things you have to remember to do, but it's not beyond a lot of people to understand. I'm sure a lot of people out there, if you're listening to this now or listening to the video recording later, you probably have heard a lot of this, but I think Eric kind of puts it all together, strings it all together, keeps it nice and basic. So I want to thank you for producing this again, Eric. Remember, we did something on recovery a couple years ago.
It's been a few years ago.
Yeah.
I think that was more than a couple.
Yeah. Is that the one where you did the 2 cameras?
Yeah, I had 2 at that point in time. I've got 2 here. I just don't move them around as much.
No, you got a better studio now. Very
Yeah,
nice.
yeah. Things have improved a little bit.
Well, you can reach us at TRUTECHTOOLS.com, True Tech Tools. Eric, do you feel comfortable sharing your email address?
Sure, you can reach out to me, Kaiser, Kaiser at TrueTechTools.com if you have questions, or our customer service team is available at support at TrueTechTools.com.
Right. And we got one final comment from American Temperature Control saying, "What's with that shirt?"
I don't know. What's with that shirt?
It's American Temperature Controls. See
See
you next week, Doug.
you, Doug. Thanks.
Okay. All right. Thanks, everyone.